All right, so I think we'll get started just so we make sure and have enough time for questions and the presentations. Good afternoon, good morning, good afternoon, good evening, depending on where you are. Today we have our November, December webinar. Because of the holidays, we do it the first week of December. So we have three presenters. We have, first we have Ahmed Cyber, and Ahmed has received his PhD degree from the University of Rikuyas, Japan in 2007. He's currently the Vice President for Optimization and AI at ETAP. He develops power system simulations tools in ETAP using both deterministic and intelligent methods. His research has been funded nationally and internationally. Manny, are you having an issue? Manny?
Maybe his sound system does not work. He can hear you, but he cannot hear us.
Okay, I'm going to mute him. All right, so his research has been funded nationally and internationally, including DOE, and he's won the IEEE Outstanding Engineer Award for Southern California and for his work in smart grid. He's also published 75 papers, has 2 patents, and his interests are in smart grid, vehicle to grid, renewables, microgrids, optimization, cyber physical, intelligent systems, and operations research. The second speaker from ETAP is Vivek Jayaraman, and he received his MS degree from Virginia Tech in 2020, a great university, and where I graduated as well, sorry. Specializes in the field of power and energy. He is currently a power engineer for ETAP with a focus on power systems.
Her voice is not coming.
Okay, he can't hear us, but we can hear him, and so anyway, we'll see what happens here. Sorry. He graduated, he's a power engineer at ETAP, and with a focus on power systems optimization, graduated with a BTech degree from NIT Trichy in India with honors, and also had assistantships at IIT Bombay, India, and the Energy Research Institute at NTU. Manny, we can hear you. I don't think his speakers are on. Anyway, current research is Volt-VAR optimization, switching optimization, fault management, service restoration with focus on their implementation in distribution systems. Okay. The other speaker, sorry, I lost her bio here. There you go. Is our last speaker is from WSU and is Rabia Khan, received her bachelor's degree from the School of Electrical Engineering and Computer Science at the University of Engineering and Technology in Lahore in 2014, and a master's degree in EECS from WSU in 2017, and currently pursuing her PhD in EECS at WSU. Her research is on DC islanded microgrids for rural, as well as optimal power flow, optimal power dispatch, and neighborhood level sharing. So with that, hopefully, Manny, can you hear us now? Oh, I don't know. So anyway, so with that, I'll turn it over to Ahmed and Vivek and Rabia. So to talk about some of our different UISys systems. Ahmed?
Yeah, thank you, Noel. Excuse me. Yeah, thanks for the very detailed bio. But the sequence is just the reverse. First, for the IIT rural feeder, Rabia Khan will present first, 15 minutes, and then IEEE 123, it means 123 node system. Vivek will present, and then I will conclude with all the summaries. So Rabia, it's yours.
Hi everyone, I'm
Check your
Rabia
speakers.
and I'm presenting about the test figures for UISs. And thank you, Dr. Schultz, for explaining and giving the bios of all of us. So I would like to explain about the benchmark system that is given to us by IIT. So the project is a collaboration among IIT Roorkee, WSU, and ETAP. So this is the benchmark system that we have obtained from IIT, and then it has different nodes, buses, and I'll explain about the system description and about the load times and different details. So the basic detail of the system is that it is a small system which is grid connected, but it is for rural areas. So the load demands are very small, and even it has multiple kind of loads. It is an unbalanced system which has both three-phase kind of loads and single-phase loads. So the load types that have been provided to us by, and it's a practical system that is being installed there, are the constant impedance loads. So there are multiple distances among the houses or among different nodes there or among different loads connected. But I couldn't explain all the distances. So the minimum distance among two nodes is 13 meters, like part of kilometer, and the maximum distance is 37.5 meter. So I can say again that it's a small system for a rural area in India. So these are the details which I would like to continue, that the rating of the transformer is 63 kVA, which transforms from 11 kV to 433 volts. And these are the impedance ratings, and the configuration is as most of the transformers are from substation to the lower level, the delta and Y grounded. And the frequency in India is different from what we have in US. In US, we have 60 Hertz, but there we have 50 Hertz. So the modeling and simulation are a bit different considering frequency according to their parameters. And these are the ratings for the grid which is connected to the system. So the single phase loads which are given to us, and I'll explain where they are located, have this ratings of 1 kilowatt and 10 watt with inductive resistance, inductive load, and capacitive load is 5 watt. However, the three-phase load is 10 kilowatt real power with 100 watt inductive load kind and 50 watt capacitive. So I'm quite sure most of us cannot consider the whole system and cannot look at all of it in detail. So I will split into small parts and will show you next that how it is formed. But if you try, if I explain, this is the grid and here's a transformer. So this part is the phase C part. This part is phase A, and from here onwards to all is the three-phase part, which I'll explain here, and I'll show the details of the system. So this is the Simulink model that we have obtained from IIT, and we have tried to model the same system in ETAP. So this is the C phase part, and it has 6 different loads connected, but each load has the same type, the constant impedance load, and each load has the same load requirements, that 1 kilowatt active power and 5 watt reactive power, and the distance among the nodes is different. However, this is the phase A part, which is connected, like we have shown on the right side of this left side on the simulation model, and it has 10 different loads connected. But again, each load is assumed to be the same with 1 kilowatt active power and 5 watt reactive power, and they have different distances among themselves. This is the three-phase part. Here we have 5 different three-phase loads connected, and each has its own rating, but all of them have the same load requirements. So we got some results from the IIT, and we tried to model the same in Simulink. Simulink results are shown here, and then we tried to model the same system in ETAP. So if you see the results of the load flow, which is an unbalanced load flow, we have different line configurations, and I'll explain. This is the source voltages with angles. These are the transformer voltages. The H1 with C, H, the alphabet H, ID with C means C phase loads. The alphabet L with IDA are the A phase loads, and TH means three phase loads. So three phase loads have all three phases, but the single phase A and C are just single phases. So that was the Simulink model, and I can show the Simulink file and run the simulation with you if you have any questions or concerns. But we have modeled the same Simulink model, simulated the same Simulink one in ETAP. So this is the overall schematic of the ETAP model, which I have formulated. And these are the same load demand requirements that we have formulated. We have assumed a constant impedance load with the same requirements as provided to us by them. And we have multiple options to display in our results, which I will explain ahead, and I can show the simulation too. So these are the results of unbalanced power flow, and we can't see and zoom into it. So I'll zoom into the actual simulation file and show you the results. So these are again the phase A part with the results, but the thing, the error, or not the error, but mainly the issue with the results we got is that we have some under voltage at the end of the load. So we had multiple options to either use the capacitor banks at here, or we can change the tappings of the transformer, or we can have PV and batteries and things like that, just to see how we can improve. So we have tried including some capacitor banks, but it's still in the future work that how we'll incorporate this phase A results. And these are the results for the phase B, C, which are for again for the unbalanced power flow. And these are the results for three-phase load, which are for the four of the three-phase loads connected, and where we have the results, and we can see how much power is flowing among the nodes, what is the voltage magnitude. We can have voltage angle as well. We can see how much is the voltage drop among two lines. So there are multiple options in ETAP which let us determine whatever we want to see. We can see voltage angles, voltage magnitudes, and power flows to the loads, and if we have capacitance, how much reactive power is being supplied, and things like that. So next, although that's most of the results, and I can switch to the simulation files if we have time and explain about the results and how we simulate them. And that is mostly my part, and I would like to acknowledge US Department of Energy and other agencies who are supporting us and helping us. So if you have questions, or if you want to let me show the simulation results, I can show that as Dr. Ahmed suggests.
Thank you, Rabia, for your good presentation. Then Vivek, would you please present your part? So now Vivek will present another system that is IEEE 123 node system, and then I will describe why we need multiple test feeders and advantage, disadvantage, those things. So Vivek, now it's yours.
Good morning. Just want to make sure my screen is visible.
You are not loud. Can you please tell a little loud?
Good morning.
Yeah,
Am I audible now?
Yeah. No, now better, much better.
Thank you. So good morning, everyone, and thank you very much for the presentation, Rabia, and for Dr. Schulz for. It's always nice to run into a fellow Hokie, to be honest. So I will be focusing on the IEEE 123 node test feeder benchmark. Now, the IEEE 123 node test feeder is runs at a nominal voltage of 4.16 kilovolts, 4 voltage regulators, and 85 lumped load. This feeder
Vivek,
is known.
Vivek, just to interrupt, can you please make full screen?
Sure.
I think full screen is better. F5.
Okay, yeah. Is this better?
Now two screens. Well, let's go the the previous one is better. Yeah, I think you are presenting from ETAP, right? You are now from that's better. That's best. Yeah.
I had two screens open, and sorry about that. So This system runs at 4.16 kilovolts and has 4 voltage regulators and 85 lump loads and 4 capacitors. Now, this system is known for its voltage drop problems, and because of this sheer size, the connectivity, how radial it is, and the number of different switches that are normally open and closed, it is possible to execute more complex ideas such as Volt-VAR optimization or switching optimization or fault management and service restoration. Now, these topics will be covered by my supervisor, Dr. Ahmed, later, but I just want to bring it up that this system is pretty much ideal for conducting more complicated scenarios. Uh, Before I move into the rest of my presentation, I want to say that a good chunk of this, the first half of my presentation, will spend on modeling how the different systems, the different components are modeled, and how they are modeled in ETAP specifically too. Now, the overhead lines, interpreting the data sheet, they have this information where you have the phasing where A, B, C, and N, or they are in different orders, and what exactly the phase conductor material is, what the neutral conductor material is, and what the spacing ID is. For example, configuration 2 has a spacing ID of 500, which would correspond to this section where phase C would be here, A would be here, B would be here, and the neutral is here. So just based on the different distances the lines are from each other, you would end up with a different configuration, impedance matrices, and so on. This is modeled in ETAP as where, for example, I have taken configuration 1. So I have phase A at 2.5 and phase B at 7 and phase C at 0. So it's basically CAB. And I have the neutral at 4 and at 24 feet from the ground. So this will help with the GMD, GMR calculations. Whereas the parameter tab that is on the right hand side will help pick the conductor type, material, the resistance. These two settings are pretty much excellent at modeling the transmission line pretty accurately within the system. As for cables, there is only one configuration present in the system that connects about 4 to 5 buses, and this is the connectivity. So in this case, it is ID 515. So it's A, B, and C between each other. And for this, we have the cable impedance matrix and the cable shunt admittance matrix in microsiemens per mile available from the datasheet. And these were modeled using a simple tab. ETAP also allows for a cable tab, but given that the system has only 5 connections between cables, and given that we have the matrices, this was a faster way of getting things done. So the system has about 85 loads, and these loads are interspersed in many ways. A lot of them are constant power loads. We have a few constant current loads and a few constant impedance loads. And this distribution also occurs with three-phase and single-phase. So in ETAP, we can model this using with the nameplate tab, where you can enter the real and reactive powers for the different phases and mention what kind of load they are, whether they're constant power, constant impedance, or constant current. Or you can even vary the percentage between the three if they happen to be a hybrid. In the IEEE 123 system, that wasn't the case, so we don't really have much of a problem. One of the more difficult approaches was that currently ETAP does not have a way where you can model a single phase load with constant current. So they are modeled as constant impedance or constant power. And in this case, we have moved forward with modeling them as constant impedance load. Uh, the next is voltage regulators, and there are 4 voltage regulators in total. This system has 2 3-phase regulators, one 2-phase regulator, and one single-phase regulator. Now, the tab independently controlled or gang operated can be used from here. So in this case, voltage regulator 5, which is 1 in the system, uh, operates all the 3 phases simply based on the measurements from phase A. And the total tab settings are plus or minus 10%. And the impedance tab that you see here right next to tab allows for R and X settings for the compensator. Uh, the system has two transformers. One of them is not explicitly drawn on the diagram of the system, but it is the substation transformer with the ratings of 5000 kVA with a 115 kV on the high side and 4.16 kilovolts on the lower side. And the other transformers between nodes 61 and 610, that is marked as XFM1, whose parameters are what I've displayed from the ETAP screenshot on the left. And that connects between 4.16 kilovolt and 0.48 kilovolts. Shunt capacitors. The system has in total 4 shunt capacitors, 3 of which are single phase, each servicing phase A, B, and C at 50 kVAr, and one 3-phase capacitor that serves 200 kVAr per phase at node 83. So here we have the capacitor editor and how it's been organized. So in total, this supplies about 600 kVA AR. The switches. These there are in total 11 switches, 6 normally closed and 5 normally open switches. The way that the system currently is set up, it allows for a radial configuration, which is good when you want to implement some distribution related load flow algorithms or optimization techniques. So these switches will be played around with when we move to switching optimization. So considering all of the different parameters and the elements, it when you model it, this is what it looks like. But I will zoom in to provide a bit of better clarity towards this. So I have only zoomed in on the left bottom section where I have the utility, the substation transformer, the substation bus that I consider to be bus 150, and a feeder or a circuit breaker that's marked as feeder, a voltage regulator, and these are the many lines that connect the different phases. We have phase adapters here where the branching off from 3-phase to 1-phase or 3-phase to 2-phase is possible, and we have the loads connected to the system. There's also one switch present here. So this pretty much covers the how the different elements will look like once you model them on ETAP. So I have simulated the unbalanced load flow results. So once I have done that, these are the results that you can see in a certain section of the system because it's just too vast. So right now the information that are displayed are the 3-phase real and reactive power consumed by the loads along with the direction of flow. So for example, if I am at 34 and the number that says 41.8 plus J20.9 in bracket C, it means that that's the real and reactive power for C phase that is consumed by the load that's attached to it. And the second parameter that I've displayed is a load terminal voltage and angle. So 102.2% is the load terminal voltage at phase C for bus 34. For a 3-phase bus, we have all the 3-phase information displayed here, which you can see in bus 195, for example. You have A, B, C voltages and the phase angles displayed right next to them. Aside from this, we have more volt display options where you can see the sequence voltages and angles, current, power factor. You can see the power in kVA instead of real and reactive, branch flow, branch loss, and voltage drop. I've chosen this just for ease of understanding how it looks like to the eye. Uh, this is another screenshot of the unbalanced load flow results, but with the voltage regulator in place so that you can see how that is displayed A and the impact of the voltage regulator. So this voltage regulator, the tap settings are 4.375%, 0.625%, 2.5%. Now, what is also obvious is that the voltage regulator works as expected because if you see the ends of the two buses, 160 and 160, just 67, sorry, you can see that 67 is a little more balanced and the voltage profile is a little bit more better than 160. So this voltage regulator helps, balance things out and keep things good. So this is the overall power flow result as seen from the feeder. Phase A consumes 1.465 megawatt, B 0.963, and C 1.194, which is largely similar to, not largely similar, almost exactly similar to what is expected of this feeder. And the power flow losses are 95.611, and we have 97.1 kilowatts. So they're again pretty much, not 97.1. Yeah, pretty much similar. The only place that there needs to be a little bit more study and focus is the difference in the kilowatt consumption, because there is a slight difference. And that can be attributed to the fact that the loads are modeled, especially the single phase constant current loads, slightly differently than what's expected. And yeah. So one of the things about the data sheet that in IEEE 123 system is that all the loads are marked as spot loads. So it is very difficult to analyze what time of the day these loads will attain their peak, or how their loading is distributed over summer or winter. So when you consider the diversity factors into account, it should be pretty important that you analyze the loading scenarios for summer, winter, day, night separately. So here I have taken an example where I've considered the scenario to be a summer, and in summer settings I have assumed constant power loads to consume a higher proportion because of air conditioning requirements than constant impedance loads, for example. So these are the settings where you can see row 4 and 5. I have altered the percentage for summer and winter to account for that. And in here it's winter loading. And for winter loading, I have assumed a higher percentage, higher contribution from constant impedance and constant current loads, because of the fact that lighting loads tend to dominate when compared to air conditioning loads, and that heating is often gas. So considering that, the winter loads for constant impedance take up a higher percentage. So when you combine everything and run the feeder summary, uh, we have the results as shown. So in summer, there is a higher consumption compared to the winter, but both of these, as such, as numbers, are lower than the design and rated, simply because the IEEE datasheet does not have any diversity factor associated with it, and everything runs at the rated, which we know in practice does not happen. So with this, I will pass the mantle to Dr. Ahmed Saber. Have any questions at this stage?
So far, so good. Do you have any question? Okay, so I cannot see anything also in the chat. All right, so now the third part. Let's share my screen. All right, so can you see my screen?
We can, but it's not large. Yeah, there you go.
Great. So yes, we have already showed two test feeders. One is IIT rural test feeder, another is IEEE 123. So if we have already test feeders, then the next stage is study. So we design all those feeders for some studies, right? Let's say what are those studies? For UI assist project, we usually have those studies like Volt-VAR optimization or CVR. There are, I think, 2 groups at least working on that. We have also system reconfiguration. Some groups are working on that reconfiguration. Also fault management, service restoration, or FMSR, sometimes we call FLIZR. Also we have, I also do load forecasting, also solar forecasting and those things. We have also battery sizing, feeder hosting capacity. Also EV scheduling, not done yet from my side. Also reliability, I did not include data, but we can also do that. Also relay coordination, even some aggregator, or also cyber security. So those studies we can run on those feeders. So yes, for specific studies we may need specific data. So we can add those things, and I'll try to describe those studies. So in IEEE 123, okay, before that, IIT rural test feeders, you have already seen that this is purely radial, and it is expected because this is rural feeder. It's purely radial, and Ravi already mentioned that we have a voltage issue at phase A. So in phase A, I have seen here sometimes voltage goes to around at the end voltage, end user 90, not 90, even 87 or something like that. That we did not expect. So we are trying to improve that. We tried to add switch capacitor or capacitor, but still, because I did not see there a lot capacitive or any inductive load there. So yes, we cannot. And then the second stage is, yes, we can add some tap in the substation side, but we need to contact with IIT. Those groups implemented that. So that part is not done yet. But the other phase like B and three-phase system, that is perfect. The voltage and everything is working very well. So that is first issue right now we have seen, but we'll solve this issue soon. Another thing I have seen that this is completely radial and we don't have, and it is expected, I already mentioned, and that's why we cannot reconfigure it. It means there is no actually switches even, so we cannot use for reconfiguration or restoration. But for other studies, that is okay. So that's why we also made another feeder that is called IEEE 123 node system. That is, yeah, obviously from IEEE, but it has, the good thing is it has loops, it has switches, it has voltage regulating devices, all those things are there. And voltage level is also pretty good there. So we can use those things also if you need, and we can run most of the studies. So right now I will show you some studies. So let's say Volt-VAR optimization. For the Volt-VAR optimization, I already ran Volt-VAR optimization on this IEEE 123 node system. But only one thing, I already mentioned that more specific, for any specific studies, we may need specific data. Let's say for Volt-VAR study, usually we run for residential load. It means mainly for constant impedance load. But I have seen in IEEE 123 node system, mostly constant power and constant PQ load or constant power load. So at least some single phase loads, actually most of the single phase loads right now I change to constant impedance load. So now I can get a very good result, and I can show you here also that the CVR factor is very good. It's 2.5%, around 2.5. It means each percentage of voltage you can, each reduction you can reduce at least 2.5% loading. That's very impressive. Let's show you some studies.
It's not full screen anymore.
That's okay. Yeah. Now I'm moving to another screen. I don't know why I cannot. Maybe I'm sharing that side.
Now it's your Teams.
Yeah, I understand. Let's first let's try different way. That's okay. When I share something, then I cannot go to my VPN. I don't know why. It cannot allow me to. I don't know how I can do this thing then. But okay. It is okay. Let me web what is it? Now that's perfect. So now you can see, right, my screen. Yeah, lucky. All right.
Yes, we can see it now.
Okay, that's perfect. So this is actually the model IEEE 123, that model in ETAP. So you can see here, yeah, we Vivek already showed you. So this is just the IEEE model, and I can run, let's the Volt-VAR optimization. So if you run the Volt-VAR optimization, you can see we can get those IEEE 123 node system. The initial loss, the initially loss without any change, it was 96.18. But after running Volt-VAR optimization, I can see here 85.89. Why? Because your initial minimum voltage was 98.81%, but the final minimum voltage is 95. That is accepted, right? 95%. That is the actually standard in USA. Then we can go until 90%. So peak saving, how much we save? Our initial power was this on around 3 meg 3.6, but I can get 3.3. So around 371 kilowatt we saved it. It is around 10%. And why? Because we change those type of taps. So we have Vivek already mentioned we have around 4 or maybe 3 or 4 voltage regulators. So we change these voltage regulator settings and we get that result. So even if you can go to less voltage, you can see when the results here, you will see for the Volt-VAR optimization, most of the end voltage will be around 95%. You see here the 95.87, here 95.56. Yeah, maybe some other locations will be around 95. But if we, some countries, sometimes they even offer not only 95, maybe we can go even 90, not 90, even around 90. And in that case, you can reduce more power. So we can go to that setting. Let's select limits. We can go 90%. I know in USA we cannot go 90%, but some countries maybe we can go 90%. So if you go 90%, even you can reach much less power. You see here 3.6 right now we can go only 3. So around 20% we can reduce the load. Around 20%. That's huge. And you see here voltage, the initial voltage is 98%, but now I went to 90%. Okay, so you see here the last voltage. Maybe it's not big, right? So here you can see voltage is 91. It is not 90 because maybe some other last or the end voltage already 90. You see here is already 90.25. So if you go here 90, if you go here 90, then it will be less than 90. So this part will be maybe 89. So that we cannot go there here 90. But okay, so that is the Volt-VAR optimization. And in this Volt-VAR optimization, the good thing is we have all the phases. We have phase A, we have phase B, we have phase C, and we have combinations A, B, B, C, C, A. So that's actually a very good unbalanced system to check our result. So which our group are, I know some groups are working with Volt-VAR optimization. So I think we can compare the results here. What we are doing and what let's do we already exist. All right, so this is let's the Volt-VAR. Okay, let's go another study. So let's, I don't know, I can go to the my presentation again back. Okay, before going to presentation even, I don't know I can come back or not. So let's show you another one. So another study is, let's say usually people like we call system reconfiguration. So for the system reconfiguration, we call switching optimization or system reconfiguration. So I'll show you the system reconfiguration one. So if you run here unbalanced load flow, already Vivek showed you. That is, let's say I assume that our system is perfect. We just run it. What is the result? But let's say I don't know our summer loading and winter loading same or not. If I know it is different for the different loading, can we expect the same configuration? May not, right? So here I showed you that the result shows that no, summer winter loading, even day night loading may be different, and that's why you can see here. So the switch number, what is SW3? So if you change the switch number 3, I think this one, if you can see this one, initially actually this is open and this is closed. But using that one, if you use different loading, then the load, the line loss may be more. So here the system shows no. If you close this switch and open this switch, it means you change this configuration. then you will increase to at least 2 kilowatt loss. Not increase, actually decrease. So it means you can gain 2.2 around, I don't know how many percentage, around 2%, 2.5 maybe, 2.2% I saw. 2.2% you can gain the line loss. So that's also good. But here one thing is, this system only we have 5 switches. So if you want, let's say for any study, if you need more, we can add more for you. Just let us know that for your study, we need more switches. We need more switches for more PDs or protective devices for relay coordination. We can add for you. All right. So this is another study. Third one is, let's say switch, we call fault management and service restoration, or FLIZR. So let's run the FLIZR. If you run through FLIZR, so let's say I have a fault here. If you go to the normal mode, so we have, let's say we have a fault here. Then what happened? Which one I'll open, which one I'll close? First of all, we need to open some switches to isolate the fault and then restore it. So let's say I run the isolation. If you isolate it, it shows that switch 6 and switch 7 we need to open. So this switch and this switch we need to open to make the system isolated. So right now the fault is isolated, but the problem is this huge load. How many? You can see here around 48 customers, or let's say each load is a customer, and 48 customers are right now out of service. So they are right now in dark. So what I need to do? Can I restore some part with let's say with maintaining all the constant? Let's see. So yes, it shows yes you can restore at least this part. You see this part is restored. At least 10 customers you can restore. Then the question is, why not all the isolated part or all the dirt people can be restored? Not, because this system has some limitation. Let's say this has some, I know this line has a thermal limit. I think it is around 100. So if you restore most of the part, then I saw this part is overloaded. So okay, what I did? So I just I did not, actually not myself, the system did not restore all the part, but it restored only this part. And also report shows everything in detail that why you did not restore all those things. So yes, so it shows that initially we lose around 48 customers, 1.9 megawatt load, but after restoration we restored 3.2 successfully. We did not restore others because of the thermal limit of this one. So this is also a good indication that if you want to restore all the part, we need to increase thermal limit of this one. We need a better cable, or some way we need to increase the thermal limit of this one. So this is another study. So I just showed 3 studies for time limitation. And if you need more studies, yes, we can run more studies for you. And if you need any more criteria or any more elements or any more data, we can add for you. I told you again that it depends on the study what we want to run. So those things, so just to summarize, we can run also system reconfiguration, and we can, because summer and winter load different, day and night loads are different, and we can around reduce 2.2% of line losses. But still we are working on the summer and winter loads, because we don't know exactly, depending on the locations and other places, depending on the load type, what should be the proper summer loading and winter loading, and we are working on that. Same thing is FLIZR. Yes, some studies may need to change the thermal limit and other things, but we just put for only one that we know. If you need different one, we can put different for those things, and we can restore maybe more customers depending on the system. So the feature work is very interesting. In this system, you already see that we don't have any PV or smart inverter. But right now, the most of the research are for PV and smart inverter for distribution system. So yes, we are right now working to add PV and smart inverters. Also battery we have in ETAP lithium ion and lead acid battery, but mainly people are working for lithium ion battery, and also we have in cell level design or model. We will also add the EVs. The good thing is in ETAP we have a rich library, and we just need to add it. The question is, if our researchers from UISCs that they need that the PV this size, and let's say we need to know the size and location. If you tell us exactly we need this amount of PV at that location, we can put it, or we just put it randomly. So we will expect some feedback from your side, and then we can add, even we can add different versions as well. So application says please use these test feeders for your study. If you need any change for any kind of study, we can add it for you. And this is the same thing, acknowledgement from UI Assist and DOE. Already Rabia and others will mention that. So yes, that's the good time for the Q&A. We are just in time. So yeah, we need feedback from you so that we can improve the feeder. Mostly right now only 2, IIT Rural and IEEE 123, but if you need more, we can also add that. Thank you.
So there are a couple questions in the chat. And since Ahmed, since you're on right now, we'll do yours first. Have you considered the inverter resources for Volt-VAR optimization? If yes, how are the injections from inverters considered at the 3-phase level or single phase?
Okay, yeah, that part belongs to me. Yeah, we have right now. We already added in ETAP. Yes, we have already smart inverter for the optimization. But in this project, we don't have any smart inverter. I already mentioned. Yes, I will add a smart inverter there. And for the smart inverter, yes, we know that for the smart inverter there is some curve, right? We have, let's say, constant. We have Volt-VAR mode. We have volt-watt mode, volt frequency mode. It has a curve, right? So in this curve, we follow this curve and then find the best setting. So yeah, smart inverter is nothing, just we need to find the best setting. For which setting we get the optimum result. Yes, we have already that. And yeah, we just follow the curve, and depending on the curve, we just find the best location, best operating point actually. Yeah, but in this project, yes, we don't have, but we will add that. But again, I repeat that, yes, in ETAP, we have Volt-VAR in Volt-VAR optimization. Yes, we include, you already, actually, if you go to the results section, you already see, 1 minute. Maybe when I take the snapshot, I switch. Yeah, we have actually here, if you can see this picture, you have loss, convention, operating, and after that we have switching, we have a smart inverter. But in this project, there is no smart inverter. That's why I did not take this picture. Okay. We can discuss also those things if we need more. Thank you. What is the second question, by the way?
The second question for you. Okay, here's a question. Can you quickly determine if phase balancing solves the thermal limitations?
I don't get this because can it be rural secondary? Which one? Indian rural. Can you say that again? For the
There's
thermal.
one from Gary Huffman, and maybe Gary can unmute and ask.
Gary, can you? Yeah.
Hey, Ahmad. When you reach a thermal limit, I know it's a radial system, but can you quickly determine if phase balancing solves the thermal limit, or is it only system upgrades that solve the thermal limits?
Yeah, that's another good question. Yes, we always say, yeah, that's a good question, Gary. Thermal limit, yes, I already mentioned that there is a thermal limit. That's why we did not restore all the customers, right? Yes, we have. We always tell that the one study cannot do all the works. Yeah, we have thermal limit reduction or thermal limit solution using feeder balancing. We call feeder balancing. Yes, in switching optimization, yes, or system reconfiguration, we have another objective. We have one objective is reduce the line loss. Second one is feeder balancing. Yes, we can also do feeder balancing, but this is another objective. Yes, we have that. Yes, we can use feeder balancing as well. Yeah. So if you yeah, using feeder balancing, yes, we can do that. Thank you, Gary. But it depends on the system. If we have sufficient number of switches, then yes, we can analyze when we model the system. Yes, we should have this capability that if something is happened, if we need to restore some loads, then yes, we should have also some feeder balancing capability.
Okay, thank you.
There's one for you, Rabia, from Sanjeev. What are the differences between secondary rural, Indian rural, and US systems? How do they compensate for the voltage drops at the end of feeder customers? And can we make rural secondary mesh at secondary level like US downtown?
So yeah, for the secondary Indian rural, the difference between the rural part and the US systems, I'm not sure. Are you asking about the frequency thing? So that is the thing that we cannot change, I believe. But besides that, the system that we have is, according to my understanding, is the one that is practically there. So if we want to make changes and make it secondary mesh, like have some reconfigurations in the system or have some connections among different lines, then I guess we can do that for a study or for improving the voltage drop or reducing the voltage drop, or have like they have installed PV system there. So we are already in progress. We have some progress with PV system installation. So we can do those things, but if we have to validate the results as it is, as we have the system, then I'm not sure. Maybe Dr. Schultz or Dr. Ahmed can suggest more, because we have that system and the first task was to validate the results with the that we have obtained from them, the IIT. So, but we can definitely make changes to improve the system. We have tried including capacitor banks in the system, and next we are going to add PV in the system and the battery then, and we'll see how that will either improve or we should switch to other possible solutions.
Yeah, and I think, Rabia, you bring up a good point that with the test systems, there's two objectives as we talk about UI assist. One objective is that we take real existing systems and we try to compare some of our modeling and simulation with the real system. And then the other aspect is taking those systems and how do we modify it? We do that a lot with the IEEE test cases, where we modify it and then we're trying to move from there. So those are good points that you bring up there. Sanjeev, I don't know if you had other questions or if that kind of answered what you were hoping.
Yeah, I think that answers my questions. Yeah, thank you.
Okay, so I want to open it up. Are there other questions?
I think we have a good number of attendee from India. So if I don't know who made this thing, and if anybody from IIT, maybe Kanpur, right? Rabia, you get these things from Kanpur, or so if you guys tell us a little bit on the at least for the phase A, the voltage is a little bit down. It is we did not model correctly, or that was the intention, or it was originally like this one. I have seen here 87% around voltage, or maybe we can contact offline.
Yeah, and I think that's one of the things we're trying to do is get those numbers and then be able to compare and contrast on what they're getting. So I believe we're working on that. So. All right. Well, thank you to our speakers today. This is our last webinar for 2021. We are looking for speakers starting in January. So, and this presentation came out at a meeting. Dr. Ahmed said, hey, well, we could do a seminar on that. So if anyone's interested in presenting particular activities, please let us know. But thanks to everybody. We wish you happy holidays and look forward to seeing you at webinar in 2022. We do have some team meetings next week with some of the leaders and researchers. So hopefully those are on your calendar. And we're still working on ones for MIT and Texas A&M. But we wish you all the best, and let us know if you have any questions on related to UI Assist. Have a great day.
Thank you.
Thank you. Thank you, everybody.
Thank you.
Thank you, Noel.
Thank you very much.
Thank you,
Thank you,
Rabia.
everyone.